Hello and welcome to the video on the mean value theorem and its applications to increase and decrease of functions. So here we have the statement of the mean value theorem from Anton's textbook and the geometric interpretation on the right hand side. Let's focus on that for a minute. So what we're saying here is we've got the interval from A to B, we've got the secant line connecting the points on the graph above A and B. Its slope is given by the change in y over change in x, so that's f of b minus f of a over b minus a. The mean value theorem states that there's got to be some point in between, at least one, for which the slope of the tangent line at that point on the graph is equal to the slope of the secant line over the entire interval from A to B. Now don't take that too lightly. That seems pretty obvious, but the mean value theorem is the most important theorem in differential calculus, as we will see. Here's one nice application of the mean value theorem. If f of t represents the position of an object at time t, then its first derivative represents the instantaneous velocity. We know that the average velocity is given by f of b minus f of a over b minus a. The derivative again gives the instantaneous velocity at c. So the mean value theorem says that these two quantities are equal to one another for some c between a and b. Now what does that mean? That tells us that there's got to be at least one time in the interval from a to b at which point the instantaneous velocity equals the average velocity over the entire interval. And that makes sense from our experience traveling in cars. For instance, say our average velocity on a certain trip is 50 miles an hour. It must be the case that our speed at some point during that trip was exactly 50 miles an hour. Doesn't mean it was 50 miles an hour over the entire trip, but at some point it had to be. It couldn't be greater than 50 the entire time or less than 50 the entire time, or that would throw our average off. Other consequences of the mean value theorem have to deal with increasing and decreasing of functions. I've just restated the theorem here and then multiplied both sides of the equation by the denominator b minus a to restate it in this format. F of b minus f of a is equal to the derivative at c, some point in between a and b, times b minus a. Now we're going to look at any two given numbers between a and b. Call them x1 and x2. The mean value theorem holds over the entire interval a to b, and therefore it has to hold on the subinterval from x1 to x2. Therefore, the mean value theorem says there must be some number between x1 and x2, we're going to call it d, for which the statement of the mean value theorem holds, and I'm recasting it in the second format. Now on the right hand side, x2 minus x1, that quantity is greater than 0 because we're assuming x2 is greater than x1. And that tells us that the algebraic sign of the right hand side is completely determined by the first derivative. So the sign of the first derivative at d determines the sign of the left hand side completely. Now what conclusions can we draw from that? Well, if the first derivative is entirely positive on our given interval, that means for any two numbers x1 and x2, we have this conclusion from the mean value theorem, and the right hand side is therefore positive in this expression, and that makes the left hand side positive because we have a product of two positive quantities. That tells us that f of x1 is less than f of x2, meaning as we go from left to right, as the x values increase, the function values increase, meaning the function's increasing. Similar statement if the first derivative is negative. Then we have a positive number times a negative number. The entire right hand side is negative. The left hand side therefore is negative, in which case the function values are going to decrease as x increases. So the function is decreasing. Lastly, if the first derivative is constantly 0, it wipes the whole right side out, and that means that the function values don't change. The function's constant on that interval. So here's just a restatement for the definition for increasing and decreasing over a given interval. Just means that the function values are going up or down or not changing as we go from left to right. And graphically, that means our graph's going uphill for increasing, downhill for decreasing, not changing height for constant functions. And here is just a restatement of what we had just concluded a minute ago, but this is a consequence of the mean value theorem. If the first derivative is positive over the entire interval, that means the function's increasing over the interval. Likewise, first derivative negative means the function is decreasing on the interval we're focusing on. If the first derivative is 0, the function's constant on that interval. Let's take a look at a couple of graphs. We're going to start with x squared. I'm using Paul Seeberger's applet here. On the left hand side, just keep your eye on the slope of the tangent line. Our graph goes from decreasing to increasing. On the left side, we see the derivative is entirely negative. The slope of the tangent line is negative here. And then right at 0, the slope of the tangent line, it becomes 0. To the right, for positive values, the function's graph is going uphill as we go from left to right. The first derivative there is completely positive. Here's x cubed. We see that graph is going up all the time. For negative values, the slope of the tangent line, the first derivative is positive. Becomes 0 right at 0, and then continues to be positive for positive x values. Alright, now in this case we're going to say that the function x cubed is increasing for all real numbers because it's increasing on the interval from negative infinity to 0 and also from 0 to infinity. So it's increasing for all real values. Okay. Now we're going to go through the steps to determine whether a function's increasing and decreasing. You want to first find all values for which the first derivative is either 0 or for which the first derivative does not exist. And we call these x values critical numbers. Then we're going to use these values found in the step 1. Those are going to partition the x-axis into disjoint intervals. Since the derivative can only be 0 at the numbers we found in step 1, or at least part of that list of numbers we found in step 1, the first derivative must be either completely positive or negative in the intervals left and right of those numbers. Right, the first derivative cannot change sign, and that tells us for us to determine whether it's increasing or decreasing on each one of those intervals, we just need to plug one number in from each one of the intervals, and then we'll know, well, it's got to be either completely positive or completely negative in that respective interval. If we happen to have two intervals that are adjacent to one another for which they're increasing or decreasing, then we want to union them together to combine it. So for instance, if our function's increasing from negative infinity to 2 and also on the interval from 2 to 8, then we're going to just combine that together and say, okay, it's increasing from negative infinity to 8. Notice in our book they allow increasing over a closed interval or an open interval. That does not contradict the definition, right? A number could be in an interval which is over which the function's increasing, and also in an interval for which the function's decreasing. We don't specify whether a function is increasing or decreasing at a point. It's got to be increasing or decreasing on an entire interval. And that concludes our discussion of the mean value theorem and the increase and decrease of functions.